Good. Greetings and welcome, ladies and gentlemen, talking about solving systems using matrices, more specifically inverses of matrices. Here's question 35 on page 103, and actually at first glance I would probably, if I had a choice, I would have solved this using elimination, because look at those y's. They're just like jumping out at me. They want to be eliminated. But that's fine. Let's figure out, all right, so matrix A is the coefficient matrix, so it's going to be a 2 by 2 matrix. So that would be 9, negative 6, 4, and 6. Matrix B is the right-hand side, or the constants, right? So that's 12 and negative 12, something to that effect. And what I'm going to do is I want to figure out, let's see, well actually, basically, I've got matrix X, which is my unknowns, which is little x and little y. And x is going to equal A inverse times B. All right, so that's what I'm looking for. So for starters, let's find A inverse. To find A inverse, I'm going to start by finding the determinant of matrix A. So to find the determinant, that would be, let's see, 9 times 6 minus 4 times negative 6. So determinants you subtract. For matrix multiplication, remember that you add your little product things. That sometimes is a point of contention there. 9 times 6 is 54, plus 4 times 6 is 24. So what's that? This looks like 78, I believe. And because this is non-zero, that implies to me that either I have infinitely, that I do have a single unique solution. So it's not that I have infinitely many or no solution, which is what could occur when I have 0 for the determinant. So to finish finding A inverse, I'm going to do 1 over the determinant, so 1/78 multiplied by, and now what I do with matrix A is I flip the location of the primary diagonal. So instead of 9 and 6 is the primary diagonal, it's 6 and then 9. And instead of, for the secondary diagonal, I change the sign. So instead of 4 and negative 6, it's going to be negative 4 and positive 6. And I realize I could distribute this 1/78 in there, but I'm not going to do it. You can't make me, because it's not going to help me out right now. I'd rather not. So x is equal to A inverse B. All right. We did some yesterday's video. We demonstrated how that came about, doing some matrix algebra there. So I'm going to take this 1/78 times 6, negative 4, nueve, and multiply that by matrix B, which was what, 12 and negative 12, was it? All right, I get a head nod there. All right, and it was a 2 by 1. Now, first of all, I want to point out that we can multiply these two things, because this is a 2 by 2 and a 2 by 1. The inner numbers match. Yay! So the outer numbers will be the size of my answer, a 2 by 1, which is the size of matrix X. It's a 2 by 1. It's wonderful news. What wonderful weather we're having. Oh, revealing the next problem there. Running out of room. I better get this done. So let's see. So X is going to equal 1/78 multiplied by, let's do multiply row by column, I suppose. Let's see, 6 times 12, is that 72, is it? Sounds right, 60 plus 12. Yeah. And plus 6 times negative 12 is negative 72. Okay, interesting outcome there. And then let's see, for the second row first column, I'll multiply the second row by the first column. Negative 4 times 12 is negative 48 plus, and like I said a moment ago, for multiplying matrices, you're adding all of your little products. For determinants, you subtract. Okay, so just want to point that out. And let's see, 9 times negative 12, so that's going to be a negative 90 plus 18, 108, I think. All right. Whoop. So let's see, that's 1/78. That's an ugly 7. There we go. 1/78 multiplied by 0, and that's going to be negative 156. And when I multiply this scalar into my matrix, each element is multiplied by it. Multiplying that by 0, oh, that's wonderful math right there. And multiplying that by negative 1/56, is that negative 2? I think it be. I think it is. So that means my answer, this is my x matrix, so little x is 0, and little y is negative 2. Or I could write that as a solution 0, negative 2 if you wanted an ordered pair as well. So that's the idea for solving a system using matrices. Now, we only know how to find the inverse by hand of a 2 by 2 matrix. So we don't know how to do that for a 3 by 3. We can find the determinant of a 3 by 3. But this next problem, problem 41 from the same page, here they've got a setup. They say, let's say you had this 3 by 3, a system of 3 equations, 3 unknowns. Here's our 3 by 3 coefficient matrix. Here's our variable matrix, a 3 by 1, and our constant matrix, a 3 by 1 as well. They said if the inverse is, now they're referring to the inverse of which matrix? They're referring to, yeah, the inverse of the, coefficient matrix, right? So they gave us the inverse. So I'm going to say that is my A inverse right there, right? Bam, A to the negative 1 is that guy. So they gave us that because I know that, let's see, oh, there's my cursor. X is going to equal A inverse times B, right? So let's see, that's going to be negative 1/9. Actually, if this, let's see, if this is negative 1/9, what was the determinant for that to be negative 1/9? Negative 9. And because, so that means the determinant of the 3 by 3 was negative 9, which we would have been able to find. That means that a solution must exist. So let's see, negative 1, a negative 2, a 1, negative 12, a negative 15, a 21, 15, 21, and negative 30 thrace. And let's see, multiplying by matrix B. So that would be negative 9, 5, and negative 1. So I've got a 3 by 3 multiplying by a 3 by 1. That's going to give me a 3 by 3. So let's see, negative 1/9 multiplied by, that might not be tall enough right there, bam. Let's see, so multiply row by column. So I'll have positive 9 plus a negative 10 plus a negative 1, right? I'll have, let's see, 12 times 9, 108 positive, plus negative 15 times 5, let's see, negative 50 plus 25, negative 75. Oh man, let's see how my arithmetic does here. Whew, I'm scared, guys. Plus negative 21, right there, bam. And let's see, 15 times negative 9, 90 and 45, negative 135. 21 times 5 is 105, if I'm not mistaken. Positivo, I guess. I didn't need the parentheses. And positive 33, because the negative 33 times negative 1. So, let's see, that's going to be negative 1/9 times, oh dear, here we go. 9 and negative 10 is negative 1, and another negative 1 is negative 2. Hopefully this has some fraction answers to it, friends. Oh boy. 108 minus 75. So 100 minus 75 is 25, plus that extra 8 would be 33, minus 21, 30 minus 9 plus 3, 14. Did I do that right? I hope so. Oh dear. Oh dear. Let's see, 33 and 21. No, it's 12, isn't it? Yeah. 12, okay. Whew. At least I caught that mistake. Yesterday's video in Math 3, I made a mistake. It was embarrassing, and now it's recorded on the internet forever. But that's fine. It's okay to make mistakes as long as we learn from them. Let's see, negative 135 and 105. That looks like negative 30 plus 33. I'm guessing that's just 3. Actually, that one wasn't as much of a guess. So let's see, let's multiply each of these by this scalar. So I'll get positive 2/9. I'll get negative 12/9, which reduces to, both of those divisible by 3, 4/3. And I'll get negative 1/3. No, yeah, 1/3. Is that the answer, I hope? Yeah, I got it. I nailed it. So that means I could write x equals 2/9, y equals -4/3, and z equals -1/3. Or I could write that as an ordered triple: 2/9, -4/3, -1/3. Graphically, what does this represent? What does this whole system represent, and what does this ordered triple represent? Does anyone know? No? If I was to write these equations out as -6x plus 5y plus 3z equals -9, that one equation would represent a plane, a flat surface, expanding out in all directions in a three-dimensional space. So each of the original three equations would represent a plane, all right? And the point that I just found, the ordered triple, would represent the common intersection between those three planes. The best analogy that I have to describe that would be, imagine you're in a room, all right? Hey, we are in a room. How crazy is that? And let's see, I've got, let's see, so here's this room. So here's a wall, and here's the ceiling. And then, bam, each of those represent their own planes, and then there's a common intersection between all three of those. It's almost like the flux capacitor right there. I like that. But I didn't bump my head on a toilet like Doc Brown did I? No. No, I did not. So yeah, so that's kind of the idea. So I've got three surfaces, right, all intersecting at a common point. That's what that represents. All right, so there's our homework. Hopefully you guys are masters of inverses of matrices, and you guys can go from there. Goodbye, Internet friends.